Good morning. Welcome to another session of AVLCom Active Video Learning Communication Series. I am Mr. Paresh Modha. I am working as an assistant professor in Eddy Patel Institute of Technology, New Vidyanagar. Today's topic is electromagnetics. See, in the last lecture we have seen some basic things about electromagnetics. We have seen various definitions about magnetic circuits, and we have also seen BH curve, right? So BH curve is basically a hysteresis curve, right? It is also known as a hysteresis curve. So today we will see which are the hysteresis losses that are occurring in the electrical systems. Today's topic are magnetic hysteresis and eddy current loss, magnetic materials, electromagnetic induction, statically and dynamically induced E.M.F.s. So before starting to the magnetic hysteresis, first I would like to show you one cognifront animation so that you can revise about the basic things of magnetic circuits. So introduction to electromagnetism. See, the objective of sessions are to define the magnetism, to classify magnets, and define magnetic poles, magnetic field, and magnetic line of force. See, whenever you are entering in the room, you might be able to see some electrical devices like refrigerator, oven, fan, tube light. So we cannot operate this device without the magnetism. So other hand, the electric appliances, the devices such as radio, telephone, ignition system of car, truck, aeroplanes are also work on the magnetism. So magnetism plays an important role in the electrical engineering. So we will see what is magnetism, what is magnetic poles. So magnetic, any substance which possesses the power of attracting pieces ion is called magnet, and the property by which it attraction take place, it's called the magnetism, right? So this one is the basic definition of magnetism. Now we will do the classification of magnet. So magnet can be classified by two types, natural magnets and artificial magnets. Natural magnets have the inherent property of attracting iron pieces. The natural magnets are like magnetite, lodestone are the natural magnets. Now artificial magnets are prepared either by rubbing iron bars with a magnet or by passing electric current through a wire which is wound around the iron piece. Here you can see that a wire is wound with an iron piece over here with a battery source. So by this way the artificial magnet will be created. That artificial magnet is called the electromagnet, and the magnetic line of force, this one is called the electromagnetism. The artificial magnets can be again divided in two parts, permanent magnet and temporary magnets. Permanent magnets are prepared from hardened steel, alloys, nickel and cobalt. The magnetism in this material is unaltered for long duration even after removal of the magnetizing force. Permanent magnets are used in earphone, loudspeaker, telephone receivers, small DC motors, etc. Temporary magnets are prepared from soft iron or nickel which retain magnetism as long as the magnetizing force is applied. Temporary magnets are used in the field of electrical generators, motors, relays, electric drives, etc. Now let's see, if we are putting a magnet in the space, so what will happen, that it will show us two direction. One is called the north direction and another one, S point, will call the south pole, or it will show us the south direction. Now this line in between the magnet, that is called the magnetic axis. So what is magnetic field? Till now we have seen about the magnets. So what is magnetic field? See, likewise in electrical field there are positive and negative charge. So likewise similar in magnetic circuit, the magnetic line, this line that is in the space or field which is a magnetic pole, will experience a force that is known as the magnetic field. So here there are so many lines in between the two magnets. Now if we want to check the property of magnet, then it can be checked by with the iron fillings. So if the magnetic field line is stronger or the magnetic field strength is stronger, so what will happen, that the iron material will be directly attract to the each other. So these are called the magnetic line of force, and it will form a closed curve, that is the line of magnetic field will be passed from N to S pole directly. It will never pass from N to S to N. So here we have, through this animation we have seen about the basics things of the electromagnetics. Okay, now we will see the magnetic hysteresis and the eddy current. So in the last lecture we have seen about the magnetic hysteresis. So what is magnetic hysteresis? Magnetic hysteresis we have seen with the hysteresis curve. Hysteresis is a characteristic of magnetic material whereby a change in magnetization lacks the application of the magnetizing force. Magnetizing force can be increased or decreased by varying the current through the coil of wire, that will be reversed by reversing the voltage polarity across the coil. We have seen this one is a solenoid in which if we are connecting with the one resistance and one battery source. Now if we give the battery voltage through the solenoid, so what will happen, we will get that is our H will increase. So what will happen, we will get the curve from 0 to A. Now if we decrease the resistance, so what will happen, see at the initially what was the condition, H and B both were 0, but as we have given the we have closed this switch and the battery is connected, so what will happen, that we will get this line 0 to A. Now if we decrease the EMF, so what will happen, on behalf of returning to this path, this point will be lies at this point, at B point, that is denoted by C. So these are called the residual magnetism. Now again if we operate this condition or operate this circuit, so what will happen, we will get this type of curve shape, that is by reversing this switch or by reversing the connection we will get this point. Again if we operate or we increase the edge, so what will happen, we will get this curve. So this whole curve is called the hysteresis loop. So this hysteresis loop can be used to find out which material is to be used. So hysteresis is referred to a situation where the magnetic flux lacks the increase or decrease the magnetizing force. Hysteresis loss is energy wasted in the form of heat when the alternating current reverses rapidly and molecular dipoles lacks the magnetizing force. So for steel and other hard magnetic material, hysteresis losses are much higher than in soft and magnetic material like iron. So this one is the steps that we have seen for the development of the magnetic hysteresis curve. Now to find out the which material is to be used, we can find out from the material that see, for example this material A is having a less area, so we can say that this material can be used for the permanent magnet. If the material is having a higher area, so we can say that it can be used for the hardcore material. So there are two losses occurring in the magnetic circuit. First one is the hysteresis losses and another one is eddy current loss. So we will now see one by one. We will see first hysteresis loss. See, the total iron loss is the sum of these two losses. So first we will see how much is the hysteresis losses that is occurring in the magnetic circuit, and then we will see how the eddy current losses are occurring. So hysteresis loss, to find out the hysteresis loss, we will take L, that is the mean length of the iron bar, that is, this one is the mean length of iron bar, A is the cross section area, N is the number of turns, B is the flux density. So what will happen, that flux that is developed in the circuit will be B into A, that is cross section area into the flux density. So when the current through the solenoid changes, then the flux will also changes, so it will produce an EMF in the circuit whose value is E is equal to N d phi by dt volt. So as we know that the value of phi, what is phi? Phi is the flux, that is B into A. So if we put the value of flux in this equation, then we will get B into A. So now what we will do, we will take N and A as a common. So what will happen, it will be d dt of B volt. Here we are neglecting the positive sign. So we have find out the voltage value. Now similarly, as we know that the losses are basically a power loss. So power loss will be V into I, or we can say that it will be E into I. So we have find out the value of E, that value of E is equal to N into A d dt of B volt. Now H is equal to Ni divided by L, right? All of we know that magnetic field strength H is equal to Ni divided by L. And the value of, if we are taking I as a main, so what will happen, I is equal to Hi divided by N. So the power loss will be nothing but it will be E into V, so it will be E into I. So as we have got the value of E is equal to Na d dt of B, and value of I is equal to Hi divided by N. So if we are putting these values, then we will get this value, that is AIH d dt of B volt. So energy, as we know that energy that is spent is in time, right? These losses are in terms of power or in terms of watt, but if we want to find out the energy that is spent, so it will be take the value of time, so with respect to time. So it will be dt is equal to AIH d dt of B multiplied by dt. So it will be AIH into dB joule, or we can say that the total net work done for one cycle of magnetizing is equal to W is equal to AI AL HB H dB joule. So all these things can be seen over here, where if we integrate this area of the loop, so what will happen, the integration area of for one cycle, it will be H into dB. So H into dB will represent the area that is shown over here, that is H dB is the area of loop, that is the area between the BH curve on the B axis only, right? So work done per cycle, if you want to find, then it will be nothing but A1 into the area of loop joule. Now AL is equal to volume of material. So net work done per cycle is equal to loop area in joule, that is WB is equal to area of BH loop in joule meter cube per cycle, right? So the precautions when we are doing the numericals, we should take the scale of B and H should be taken into the consideration while calculating the actual loop area. For example, if the scales are 1 centimeter is equal to x AT per meter for H and 1 centimeter is equal to y Weber per meter square for B, so what will happen, that WB is equal to xy in bracket area of BH loop, that will be in terms of joule per meter cube per cycle. Now let's take one example based on the hysteresis laws. See, in this example, the hysteresis loop for a certain magnetic material is drawn to the following scale. Here it is 1 centimeter is equal to 280 per meter, and for the y axis 1 centimeter is equal to 0.1 Weber per meter square. So which are those values? See, these are this value, that is the value of B and value of H. In the x axis the H is taken and in the y axis B is taken. So from this you can plot the graph. So the area of the loop, the total loop area is equal to 48 centimeter square. Now here you have to assume that the density of material is 7.8 multiplied by 10 raised to 3 kilogram per meter cube, and you have to find out that how much will be the hysteresis losses at the 50 hertz system or at the 50 hertz supply. So the solution is that hysteresis loss, as we know that it is xy, right, and the area of BH loop. So as in the data it is given that it is a 1 centimeter is equal to 280 per meter, and y axis is equal to 1 centimeter is equal to, so what will happen, it will be 1 centimeter is equal to 0.1 Weber per meter, and x is equal to 200 and y is equal to 0.1. so the area of loop, as it is given, it is 48 centimeter square. So if you want to find out the losses, then we have to put the value of x, value of y into the area of loop, and we have to consider the density of the material as a 7.8 into 10 raised to 2 kilogram per meter square. So volume of 1 kilogram material is equal to mass divided by density. So the losses, that is hysteresis losses, will be 960 multiplied by 1 divided by 7.8 into 10 raised to 3 joule per cycle, and the losses will be 960 multiplied by 50 is the frequency, and if you are putting the other values, then you will get the hysteresis losses. Hysteresis losses is 6.15 watt per kilogram. So these are the losses. So these hysteresis losses will basically generate the heat, and as it is generating the heat, so what will happen, the temperature of the material will get increased. So if it is generating 6.15 watt of heat in the material, then what will be the output that you should consider? Okay, we'll take another example. Here also you have to find out the hysteresis losses in an iron core weighting of 50 kilogram having a density of 7.8 into 10 raised to 3 kilogram per meter cube. When the area of the hysteresis loop is 150 centimeter square and frequency is 50 hertz, and the scale on x and y axis are 1 centimeter is equal to 30 ampere turn per centimeter, and y axis scale is equal to 1 centimeter is equal to 0.2 Weber per meter square respectively. So how you will find out the hysteresis losses in this example? See, first thing is that you have to find out the area, right? So how you can find out the area? The x and y axis data are given to you.